Good afternoon. This is Clara. I work for Intel as a senior principal engineer on standards, and I also serve as IOWN Global Forum's Technology Steering Committee chair. Today, in this talk, I'm serving at my IOWN Global Forum Technology Steering Committee chair duty, and together with Kurebayashi from NTT, we will introduce IOWN and especially its how it enables efficient infrastructure for AI analysis. Okay, so I will first give introduction on the forum, and then I will hand over to Kurebayashi to talk about the AI work. So about the forum, so IOWN stands for Innovative Optical and Wireless Network. So its goal is to enable the next generation optical transport network with order of magnitude improvement on latency, energy efficiency, and overall performance. And then because this high-speed optical transport network, it will also transform how we do computing and how we support different workloads. So this is also what IOWN will look into. So from its inauguration in 2020, IOWN has now has more than 130 members spanning from telecom operators, equipment manufacturers, software providers, and end users. So Red Hat is also a sponsor member and a board member of IOWN Global Forum. So IOWN is taking a full stack approach. So in the bottom of stack, there's open photonics network, and there's a data-centric infrastructure, which is a computing platform. And on top, there are different workloads spanning of different segments. So one fundamental technology of IOWN is the open photonic network. So what it do is disaggregate the traditional rodent node into span, leaf, and set, so that we can extend the optical network to the very end of the customer side. And in this way, the range of the all photonic network will be expanded, and so that we will achieve great reduction in the latency and also achieve net energy saving because of the reduction of the optical to electrical node transformation. So another fundamental technology of IOWN is the data-centric infrastructure. And so what it do is it enables disaggregated and heterogeneous computing infrastructure with technologies such as dynamic bare metal node composition, and accelerator pooling and sharing within data centers and also across data centers, and also intra data center and inter data center remote memory access over all photonic network. So with this, I hope you got overall understanding of what IOWN is doing. And then now I will hand over to Kurebayashi to talk about how IOWN supports AI analysis.
Okay, thank you. Okay, so I'm Ryosuke from NTT, and I'd like to talk about real-time AI analysis at the regional edge cloud with IOWN technologies. In IOWN Global Forum, we have been conducting many POCs to demonstrate the feasibility and the effectiveness of IOWN technologies. And today's my presentation is about the outcome of one of such activities. So this slide shows the use case we are assuming in our POC, and this is a typical cyber physical system use case to continuously analyze a large number of sensor data streams at the remote computing sites to enable prompt action and automation. This use case can be applied to many fields, such as area management and industry management and mobility management. We are assuming no less than 1,000 video cameras and or LiDAR sensors are installed at the monitored area, and the sensor data from them are aggregated and transferred to regional edge cloud to perform a real-time AI analysis efficiently. So one of the key design choices to implement this use case is where we should place AI function. You may want to place AI function at a large-scale cloud. It may work for certain type of AI workloads, such as batch processing. But due to high latency and overheads associated with collecting large amounts of data, it would be difficult to provide services with strict low latency, strict lead time performance. So placing AI function to monitor the area increase maintenance costs to upkeeping on board new AI models and additional hardware. So there is a trade-off between real-timeness and cost. So that's why utilization of edge data center has been discussed for years, but it still has several issues such as land and power shortage in metropolitan and urban areas, or fewer scale of merits at rural area. So we believe IOWN technology can be a good solution to resolve these issues. IOWN APNs are low latency and lossless communication, and DCI's accelerated data pipeline enables extending the low latency capability of edge computing to more remote locations. We call it a regional edge cloud. It will also allow a regional edge cloud to make use of local available renewable energy at suburban or rural areas. So this IOWN POC of real-time AI analysis was supported by 4 companies: NTT, Red Hat, NVIDIA, and Fujitsu. Fujitsu provided physical computing nodes, and NVIDIA provided accelerator-related technologies such as GPU, SmartNIC, and DPIPU. Red Hat provided container-related technologies, OpenShift for x86, and Microshift for DPIPU. NTT integrated these technologies and provided workloads utilizing data plane acceleration technologies and IOWN testing environment, including APN, for the evaluation. So NTT and Red Hat just issued a joint press release last month, and we have posted a detailed POC report to the IOWN Global Forum official site. So you can learn more about this POC from this site if you are interested. And in today's presentation, I'd like to highlight some of the points of this POC. So before going to show our approach, I'd like to point out several issues in conventional AI workloads. Usually, computing sites for monitored area and AI analysis is connected via conventional IP network. And their data transferring and data processing follows a so-called CPU-centric manner. So the latency of IP network and overheads in protocol processing in OS kernels and data transferring between host and NIC GPU can be bottleneck in large-scale sensor data collection and analysis. In addition, the range of the usage of acceleration is limited. Usually, only inference process is offloaded to GPU. So we can say there is more room for performance improvement by fully leveraging the capabilities of accelerators. So in our accelerated AI workloads, we assume the two computing sites are connected via IOWN APN. So we can utilize its lossless communication and low latency communication capability. To achieve accelerated data pipeline for AI inference, we adapted RDMA over APN to directly fetch a large-scale sensor data from local sites to the memory in an accelerator in a remote data center. This way reduces the protocol handling overheads in the conventional network, and also we adapted a full offloading of AI workloads to GPU, so we can complete full AI process within accelerators, and this way improves the power efficiency significantly. We also, to support a large-scale AI data analysis in real time, we employed a Red Hat OpenShift, supporting Kubernetes operators to hide the complexity of implementing hardware-based accelerators, and it enables improved flexibility and easier deployment across disaggregated sites, including remote data centers like regional edge cloud. So this shows the overview of our demonstration system. We evaluated AI workload with Yokosuka City as the monitored area and Musashino City as the regional edge cloud. Both are connected via APN, and the distance is approximately 100 kilometers. As a result, we confirmed the latency required to aggregate sensor data for AI analysis of our accelerated AI workload was reduced by 60% from the conventional AI workload. And also the power consumption of AI analysis for each cameras was reduced by 40%. So this shows the experimental result of the latency, and you can see the latency was reduced from around 50 milliseconds to less than 20 milliseconds. And this is the experimental result of throughput and power efficiency. And for lightweight AI model, Yorotiny, the power consumption was reduced by 40%. And as for heavy AI model, the power consumption reduced by around 30%. And our accelerated data pipeline for AI can streamline the data flows among CPUs and GPUs. So it allows GPUs to be scaled up to accommodate a larger number of cameras without the CPU being a bottleneck. So as a result of trial calculation, assuming accommodation of 1,000 streams, it is expected that the power consumption can be reduced 60%. Okay, this is the last slide of my presentation and future work. In this presentation, we used x86 servers, so now we are testing a DPU IPU with Microsoft for more efficiency. And also, we are going to demonstrate a flexible scaling of accelerated data pipeline with composable disaggregated computing, and this topic will be discussed in a Tuesday session in KubeCon. And we are aiming to achieve a heterogeneous accelerator chaining from various vendors in a vendor-neutral way. And this topic will be discussed in a tomorrow session. So if you are interested, please join this session as well. Thank you for your kind attention.